This is sleep science drift, a place for slow thoughts and slower breathing at the end of a long day. Maybe you came here to unwind, or maybe you simply like the feeling of drifting into something too small and too strange to fully picture while your room goes dark. Either way, settle in. There is nothing for you to do now except listen. Tonight, we travel somewhere smaller than any place we have visited before. Down past the atom, into the quiet, uncertain world of quantum physics. A realm where particles behave like waves, where looking changes what is seen, and where the smallest pieces of the universe keep their secrets until the last possible moment. If these quiet journeys help you rest, and you would like more of them, consider subscribing to Sleep Science Drift. It is a small thing, and it helps others find their way here too. Now, let's begin. Everything you have ever touched is made of atoms, and every atom is mostly empty space. If a hydrogen atom were the size of a cathedral, its nucleus would be smaller than a grain of dust floating at the center. The rest is a hush of possibility, where a single electron might be. Down at this scale, the tidy rules of falling apples and rolling stones quietly stop applying. A new set of rules takes over, softer and stranger, and tonight we let them in. There is no wall between the ordinary world and the quantum one, only a gradual fading. Baseballs and coffee cups are so large and made of so many particles that their quantum strangeness averages itself into calm, predictable behavior. But a single electron, alone, has no crowd to hide its strangeness in. It is free to be uncertain, to be smeared out, to be more than one thing at once. Somewhere between one particle and 1 trillion, the world slowly learns to behave. For centuries, light was thought to be simply a wave, spreading outward like ripples on a pond. Then, quietly, scientists noticed that light also arrives in small, indivisible packets. These packets are called photons, and each one carries a fixed, specific amount of energy. You cannot have half a photon, any more than you can have half a heartbeat. Light, it turned out, was never only a wave, and never only a particle, but something patient enough to be both. The word quantum simply means a fixed, discrete amount, the smallest unit something can come in. Before this idea, most quantities in physics were thought to flow smoothly, like water from a tap. Energy, it turned out, is not like that at all down at the smallest scales. It arrives in steps, in small parcels, never in between. The universe, at its root, seems to prefer counting to pouring. In the year 1900, a German physicist named Max Planck was trying to solve a stubborn puzzle about glowing hot objects. The old equations predicted something absurd, an infinite amount of energy pouring out of every warm object. Planck found that the numbers only worked if energy came in small, discrete packets, rather than a smooth stream. He called this smallest packet a quantum, and treated the idea as little more than a convenient trick. He had no way of knowing he had just opened a door that would never close again. A young Einstein, still working quietly in a patent office, took Planck's small packets seriously. He proposed that light itself was made of these packets, later named photons, and not simply a continuous wave. This explained a puzzling effect where shining light on certain metals could knock electrons loose, but only above a certain color, no matter how bright the light was. Brightness added more photons, but only the right color carried enough energy in each one to do the work. It was for this quiet insight, and not for relativity, that Einstein later received his Nobel Prize. If light, a wave, could behave like a particle, a young French physicist wondered if the reverse might also be true. Louis de Broglie proposed that every particle of matter, even you, carries a hidden wave alongside it. For a person walking across a room, that wave is so impossibly short that it changes nothing you would ever notice. But for an electron, the wave is large enough to matter, large enough to bend, to spread, to interfere with itself. Everything, it turns out, carries a quiet rhythm most of us are simply too large to hear. It is natural to ask what, physically, is waving when a particle behaves like a wave. The honest answer is strange and a little humbling even for physicists. What waves is something called a probability, a mathematical description of where a particle is likely to be found. Not a wave in water or in air, but a wave in possibility itself. Reality at this scale is written first as a set of chances and only later as a single fact. In the 1920s, scientists fired a beam of electrons at a thin crystal, expecting them to scatter like tiny bullets. Instead, the electrons formed rings and patterns, the unmistakable signature of a wave passing through a fine structure. Solid, familiar electrons, the same particles that quietly power every light in your home, were behaving exactly like ripples of light. The experiment confirmed de Broglie's strange idea beyond any reasonable doubt. Matter, it seemed, had been keeping a secret rhythm all along. This dual nature is not a contradiction that physics later resolved, but a permanent feature of how small things behave. An electron is never secretly a wave pretending to be a particle, or a particle pretending to be a wave. It is something else entirely, something our everyday language was never built to describe. We borrow the words wave and particle because they are the closest shapes our minds already know. The truth, most likely, has no shadow on our familiar wall at all. When two ripples on a pond meet, they can add together or cancel each other into stillness. This gentle blending is called interference, and it is the clearest signature that something is a wave. Light shows this constantly, in the shimmer of oil on wet pavement, in the soft colors of a soap bubble. Electrons, protons, even whole atoms have been shown to interfere with themselves in careful laboratories. Somewhere in that quiet cancellation and addition, the quantum world hides its clearest fingerprint. By the late 1920s, the wave and the particle had been sitting together long enough that physicists needed a fuller picture. They needed to understand not just that small things behaved strangely, but what happens when we try to watch them do it. That question would lead to one of the most quietly famous experiments in the history of science. A simple wall, two narrow openings, and a question about what watching does to the world. Let us walk toward it slowly. Long before quantum physics existed, a scientist named Thomas Young shone light through two narrow slits cut into a screen. On the wall behind, instead of two bright stripes, he saw a whole pattern of light and dark bands. This was proof in 1799 that light behaved as a wave, spreading and overlapping through both slits at once. It was elegant, it was simple, and for over a century it was considered fully understood. No one yet suspected what would happen when the experiment was repeated with single particles, one at a time. In the 20th century, physicists repeated Young's experiment, but this time firing electrons one at a time toward the two slits. Common sense suggests each electron should simply pass through one slit or the other, landing directly behind it. Instead, after enough electrons had been fired, one by one, the same wave-like pattern slowly appeared on the far screen. Each single electron, alone in the apparatus, seemed to pass through both slits at once, interfering with itself. It is one of the strangest sentences in all of physics, and it is simply true. Naturally, physicists wanted to know which slit each electron truly passed through. So they placed a small detector beside the slits, gently watching, without touching anything else about the setup. The moment they did, the interference pattern vanished, replaced by two simple stripes, exactly as common sense expected. Simply gathering the information of which path was taken was enough to collapse the wave-like behavior into particle-like behavior. The universe, it seems, answers differently depending on whether or not we are listening for an answer. It is tempting to imagine that human consciousness is somehow required to collapse this pattern, but that is not quite right. Any interaction that records which path information will do, a detector, a stray particle, even the environment itself. What matters is not a mind observing, but information about the path becoming real anywhere in the universe. Once that information exists, even unread, the interference is already gone. The mystery is not about minds watching, but about knowledge quietly settling into place. In an even stranger twist, physicists arranged an experiment where the choice to measure the path could be made after the particle had already passed the slits. Astonishingly, the later choice still determined whether interference appeared or not. It is as though the particle's past behavior adjusts itself based on a decision made after the fact. Physicists are careful here, since nothing actually travels backward in time to change events. But the experiment reminds us how gently our simple notion of before and after bends down at this scale. The double-slit experiment has since been repeated with atoms, and even with whole molecules far larger than a single particle. Buckyballs, cage-like molecules made of 60 carbon atoms, have shown the same soft interference pattern. Each molecule, complex enough to have its own faint shape, still passed through both slits as a wave of possibility. Somewhere beyond that size, the effect fades, lost in the noise of a large, busy world. But the boundary keeps moving further out. Every time, our instruments grow quieter and more careful. Physicists sometimes call the double-slit experiment the heart of quantum mystery, and it has earned that name. It shows, cleanly and simply, that a single particle can hold multiple possibilities at once. It shows that observation is not a passive act, but something that quietly shapes the outcome. And it shows that our instinct to ask which path is real may simply be the wrong kind of question. Some mysteries, it turns out, are not solved, only gently understood from a new angle. It is worth pausing here, because this experiment tends to unsettle people the first time they truly sit with it. That unsettled feeling is a reasonable response, not a sign that something is being misunderstood. Even Richard Feynman, one of the most gifted physicists of his century, said this single experiment contains the whole mystery of quantum physics. You do not need to resolve it tonight, or ever, to find peace with it. Some doors are simply meant to stay open a little, letting the mystery breathe. Before a particle is measured, it does not sit quietly in one definite state, waiting to be noticed. Instead, it exists in something called a superposition, a gentle overlap of every state it could possibly be in. An electron might be spinning one way and the other way at once, not switching quickly between them, but holding both. Only when it is measured does it settle, apparently at random, into a single definite outcome. Until then, the universe seems content to leave the question politely unanswered. It is easy to assume superposition is just our own ignorance, that the particle secretly already has one answer, and we simply have not learned it yet. For decades, many physicists, including Einstein, hoped this was the case. But careful experiments have shown this is not true. The uncertainty is not hidden information. It is built into the fabric of reality itself. The particle genuinely has no single answer until the moment it is asked. Nature, it seems, is comfortable with a kind of not knowing that goes deeper than our own. Many particles carry a property called spin, though it is not quite the spinning of a top or a coin. It behaves more like a tiny, built-in compass needle, pointing in a direction that can be measured. Before measurement, this needle can point up and down at once, a true superposition of directions. Only the act of checking forces a single direction to appear. It is a small, quiet needle, holding two answers until the last possible instant. Physicists describe a particle superposition using something called a wave function, a mathematical description of all its possibilities. The wave function does not tell you what will happen, only how likely each outcome is. It evolves smoothly and predictably over time, like ripples spreading calmly across still water. Then, upon measurement, something strange happens. The smooth spread of possibility instantly gives way to a single, sharp fact. Physicists call this sudden change collapse, though no one fully agrees on what collapsing truly means. Imagine a coin spinning gently in the air, neither heads nor tails while it turns. In our ordinary world, this is simply a blur, a fast alternation we cannot quite see. In the quantum world, the coin genuinely is both heads and tails together until it lands. The landing itself, the measurement, is what forces a single answer into being. Before that quiet landing, both futures exist, side by side, equally real. Superposition is not only theory, it has been demonstrated directly in careful and patient laboratories. Scientists have placed tiny objects, single atoms, and even microscopic metal drums into superpositions of vibrating and not vibrating at once. These experiments require extreme cold and extreme quiet, since any small disturbance destroys the delicate overlap. Yet, for a brief moment, the object truly exists in two states simultaneously. It is a fragile kind of magic, one that vanishes the instant the world leans in too closely. If superposition is real, a reasonable question follows. Why do we never see large objects in two places at once? The answer lies in a gentle process called decoherence, where a delicate quantum state leaks its secrets into the surrounding environment. Every stray photon, every air molecule that brushes against an object, quietly carries away a small piece of information. Once enough information has leaked out, the superposition effectively collapses, whether or not anyone is deliberately watching. Large objects are simply too exposed to the world to keep their secrets for long. One way to picture superposition gently is to imagine every possible outcome as a soft, overlapping thread. Before measurement, all these threads exist together, quietly woven into one shimmering whole. Measurement does not create a new thread. It simply reveals which one becomes the story we experience. Whether the other threads vanish or continue elsewhere is a question physics has not fully settled. For now, it is enough to know that possibility itself has texture and weight. Though it feels abstract, superposition already shapes ordinary technology all around you. The precise, steady ticking of atomic clocks depends on carefully controlled quantum superpositions inside atoms. These same clocks quietly keep the timing accurate for satellite navigation, guiding ships and phones alike. A phenomenon once considered too strange to be real now helps you find your way home. The strange and the useful, it turns out, are not so far apart. There is something quietly comforting in superposition if you let yourself sit with it. Not every question needs an immediate answer. Not every possibility needs to be resolved right away. The universe itself seems willing to hold multiple futures gently, without rushing to choose. Perhaps for tonight, you can hold your own unresolved thoughts a little more gently too. Let them overlap, softly, unmeasured, until morning decides to ask. In 1927, a young physicist named Werner Heisenberg discovered something that would reshape all of physics. He found that certain pairs of properties, like a particle's exact position and its exact speed, cannot both be known perfectly at the same time. This is not a flaw in our instruments, waiting to be engineered away. It is a fundamental limit, woven into the structure of nature itself. The universe, quietly, keeps a small and permanent secret from every observer. The more precisely you pin down where a particle is, the less precisely you can know how fast it is moving. And the more precisely you measure its speed, the blurrier its location becomes. It is a gentle trade-off. Sharpening one detail always softens the other. No clever trick or better microscope has ever managed to escape this rule. Nature seems to insist that some knowledge always comes at the cost of some other. For years, people assumed uncertainty simply meant that measuring a particle disturbed it, like touching a soap bubble to check its size. That old explanation, while intuitive, is not the deepest truth. Even with a perfectly gentle, disturbance-free measurement, the uncertainty would still remain. It is not clumsiness that limits us, but the very definition of what a particle's properties mean. Some things simply do not have sharp values until we choose which one to ask about. The uncertainty principle applies to other pairs of properties too, including energy and time. Over a very short span of time, the energy of a system can be remarkably uncertain, blurred and fluctuating. This blurring allows for strange, brief borrowing of energy from seemingly empty space. As long as the borrowed energy is returned quickly enough, nature does not seem to mind. Even emptiness, it turns out, is allowed a little flexibility for a moment. Heisenberg himself described this principle with a quiet kind of humility, rare among great discoveries. He suggested that nature simply forbids certain questions from having sharp, simultaneous answers. Not because we lack the tools to measure carefully enough, but because reality itself declines to specify. It was a strange comfort to him, in a way, that the universe had firm and knowable boundaries, even if they were boundaries on knowledge itself. Some limits, once accepted, stop feeling like walls and start feeling like quiet architecture. One gentle way to think of uncertainty is to imagine the universe refusing to draw its outlines too sharply. a particle's position is less like a single dot and more like a soft, fading cloud of likelihood. Its edges blur gently outward, never quite resolving into a hard boundary. This softness is not a failure of description. It is simply how reality is built. Perhaps it is fitting that the smallest scales of existence refuse to be pinned down too tightly. Strangely, this fuzziness is part of why atoms do not collapse in on themselves. If an electron's position were perfectly known, its momentum would become wildly uncertain, giving it enormous, restless energy. This restless energy keeps electrons from spiraling all the way down into the nucleus. The very fuzziness that once seemed like a limitation is what holds matter together. Without uncertainty, atoms and everything built from them would simply not exist. Before quantum physics, many scientists believed that with enough information, the entire future of the universe could, in principle, be calculated exactly. The uncertainty principle quietly closed that door forever. Even with perfect knowledge of the present, the future remains genuinely, fundamentally uncertain. Not because we are missing information, but because the information itself does not fully exist yet. The universe, it turns out, is still quietly writing its own story as it goes. There is a kind of peace available in accepting that some things are not meant to be pinned down completely. The universe itself does not demand perfect certainty before it continues turning. It moves forward gently, comfortable holding fuzzy edges and soft unknowns. If the smallest particles can rest in uncertainty without falling apart, perhaps we can borrow a little of that same ease. Some questions are simply allowed to stay soft, unanswered, until sleep quietly answers them for you. Imagine rolling a ball gently toward a hill too tall to climb over. In our everyday world, without enough energy, the ball simply rolls back down every time. In the quantum world, a particle occasionally appears on the other side of the hill anyway, without ever climbing over it. This strange passage is called quantum tunneling, and it happens more often than most people realize. Sometimes, in this small and gentle universe, walls are more like suggestions. Tunneling works because a particle is never truly a small hard ball, but a spread-out wave of probability. Part of that wave always leaks slightly beyond a barrier, even one the particle should not have enough energy to cross. If that faint leaking wave reaches the far side, there is a small but real chance the particle appears there. The particle does not break the barrier or fly over it. It simply appears where its wave still gently reached. Even the most solid-seeming walls have a little softness if you look closely enough. Quantum tunneling is not just a laboratory curiosity. It is part of why the sun shines at all. Deep in the sun's core, hydrogen nuclei should, by classical physics, repel each other too strongly to ever merge. Yet tunneling allows a small fraction of them to slip past that repulsion and fuse together. This fusion releases the warmth and light that reaches you, gently, across 93 million miles of space. Every quiet, sunlit afternoon you have ever felt began with a tiny act of tunneling. Tunneling is not confined to stars. It happens quietly within living things as well. Some enzymes, the tiny machines that keep your cells running, appear to use tunneling to move particles more efficiently than classical physics would allow. Electrons and even small hydrogen particles slip through barriers inside these molecular machines. The exact details are still being studied, gently and carefully, by biologists and physicists together. Somewhere inside you tonight, tiny impossible journeys may already be quietly taking place. Engineers have learned to harness tunneling directly, rather than simply observing it in nature. The flash memory inside phones and computers stores information using carefully controlled tunneling of electrons. A microscope called the scanning tunneling microscope uses the same effect to trace the surface of materials, one atom at a time. It can produce images so precise that individual atoms appear as gentle, rounded bumps. A phenomenon once thought impossible now quietly helps us see the smallest shapes in the world. Some atomic nuclei are unstable and eventually release a small particle in a process called radioactive decay. For decades, physicists wondered how that particle ever escapes the immense force holding the nucleus together. Quantum tunneling gave the answer. The particle's wave slowly leaks outward, until, at some unpredictable moment, it appears free. This is also why radioactive decay is fundamentally random. No clock or countdown exists inside the nucleus. Only a quiet, patient probability, waiting for its moment to become real. You cannot know exactly when a single unstable atom will decay, only the odds that it will happen within a given time. Given enough atoms, this uncertainty smooths into a reliable average, known as a half-life. But for any one particular atom, the moment of decay is genuinely, irreducibly unknown in advance. It is one of the few truly random processes known to exist in nature. Even the oldest atoms in the universe still carry a quiet, patient uncertainty about their own next moment. Physicists have even measured, in careful experiments, how long a tunneling particle appears to spend inside the barrier itself. The results are strange, suggesting the particle spends less time there than intuition would expect. Some interpretations suggest tunneling particles move, in some sense, faster than light through the barrier, though nothing here violates relativity. This remains an active and gentle debate among physicists studying the deepest corners of the theory. Not every mystery in physics has been folded neatly away just yet. You might think of tunneling as a quiet kind of hope built into the structure of matter itself. Even facing a barrier that seems impossible to cross, a small chance of passing through always remains. Nothing guarantees the crossing will happen, but nature never fully closes the door either. Somewhere in every stubborn wall, a faint wave of possibility keeps gently leaking through. Perhaps that is a small, comforting thought to carry with you towards sleep. Tunneling is far more common at the scale of atoms and particles than at the scale of everyday objects. In principle, you yourself could tunnel directly through a solid wall, given enough patient waiting. The odds, however, are so vanishingly small that you could wait far longer than the current age of the universe and never see it happen. The effect is real, but reserved almost entirely for the smallest, lightest travelers. For tonight, your own walls remain gently, reliably solid. We have wandered through sunlight, radioactive atoms, and the quiet machinery inside living cells. All of it connected by the same soft, patient rule that barriers are never quite as final as they appear. Now we turn toward an even stranger idea, one involving particles that remain connected across impossible distances. A connection so strange that Einstein himself once distrusted it entirely. Let us drift gently toward it now. Sometimes two particles can be created together in such a way that they remain deeply linked, no matter how far apart they later travel. This link is called entanglement, and it is one of the strangest, gentlest ideas in all of physics. Measuring one particle instantly tells you something certain about the other, even if it is on the far side of a galaxy. Nothing physical travels between them in that instant, and yet the connection is completely real. It is as though the universe occasionally ties a quiet knot between two distant threads. Einstein found this idea deeply uncomfortable and famously called it spooky action at a distance. He believed the particles must simply carry hidden, preset answers agreed upon at the moment they were created. For decades, this seemed like a reasonable, calming explanation. But later experiments proved this hidden agreement idea to be impossible. The connection is deeper and stranger than any preset answer could explain. Even one of history's greatest minds needed time to make peace with this particular mystery. In 1964, a physicist named John Bell devised a clever mathematical test to settle the argument. His test could distinguish between Einstein's hidden, preset answers and true, deep quantum entanglement. Decades of careful experiments have since confirmed, again and again, that entanglement is the real explanation. No hidden answers, no secret agreement made in advance, only a genuine and mysterious connection. Some questions in physics take generations to answer gently, but they do get answered. It is important and reassuring to know that entanglement cannot be used to send messages faster than light. Although the connection is instant, the results of measurement still appear random to each observer alone. Only when the two distant results are later compared, through ordinary and slower communication, does the strange correlation become visible. Relativity's gentle speed limit remains fully intact, undisturbed by this quiet quantum connection. The universe keeps its rules consistent, even while keeping its secrets strange. Entangled particles are usually created together from a single shared event or source. A single photon of light, for example, can sometimes split into two entangled photons of lower energy. These two new photons carry a shared, linked identity, even as they travel off in entirely different directions. Measuring the polarization of one instantly determines the polarization the other must have. Born together, they remain quietly bound, no matter how far their separate paths may lead. Scientists have tested entanglement across remarkable distances, including between ground stations and an orbiting satellite. In one experiment, entangled photons were sent to two locations over 700 miles apart. The strange quantum correlation held perfectly, undisturbed by the vast gap of open sky and space between them. Distance itself does not seem to weaken or dilute this particular kind of connection. Whatever entanglement truly is, it appears to care very little about how far apart its two halves may wander. Entanglement is not only mysterious, it is also remarkably useful, especially in the emerging field of quantum computing. By linking many particles together in entangled states, a quantum computer can explore many possibilities in parallel. This gives it the potential to solve certain problems far faster than any ordinary computer ever could. The strange knot Einstein once distrusted has quietly become one of technology's most promising threads. We will return gently to this idea a little later tonight. Entanglement also allows for something called quantum teleportation, though it is gentler and stranger than the word suggests. No object physically vanishes and reappears elsewhere. No matter transports through space. Instead, the precise quantum state of one particle is transferred onto another, distant, entangled particle. The original state disappears from the first particle the instant it appears on the second. It is less like traveling, and more like quietly passing a fragile secret from one hand to another, across any distance at all. Quantum teleportation still requires ordinary, slower communication to complete the process, so it cannot outrun the speed of light either. It has, however, been successfully performed with photons, atoms, and even small groups of particles in laboratories. Teleporting an entire person, with all the complexity of every atom involved, remains far beyond current or foreseeable technology. For now, this gentle transfer of information remains reserved for the smallest travelers. Some journeys are simply meant to stay small, quiet, and precise. You might think of entanglement as two candles, lit from the very same flame long ago. Though carried to opposite ends of the world, something quiet in each still remembers the other. Not a message passing between them, simply a shared origin that never fully lets go. Perhaps some connections in your own life feel a little like that too, distance mattering less than the quiet shared beginning. Let that thought settle gently as we drift toward our next quiet mystery. In 1935, physicist Erwin Schrödinger proposed a strange thought experiment, not to describe reality, but to question it. Imagine a cat sealed inside a box, along with a tiny radioactive atom, a detector, and a vial of poison. If the atom decays, the detector triggers, releasing the poison, but the decay itself is a quantum event, genuinely uncertain until observed. By the strict logic of quantum superposition, until the box is opened, the atom is both decayed and not decayed at once, which would seem to mean the cat inside is, in some strange sense, both alive and not alive, simultaneously. Schrödinger did not believe his cat was truly both alive and not alive, and he was not proposing this as literal reality. He was pointing out how strange it becomes when we apply quantum rules, meant for tiny particles, to something as large as a cat. The thought experiment was a gentle challenge, almost a complaint, aimed at the strangeness of his own field. It remains, nearly a century later, one of the most quietly famous images in all of science. Sometimes the clearest way to explain a mystery is to build an even stranger one beside it. In reality, a cat is made of an almost uncountable number of particles, constantly interacting with air, light, and warmth. This constant interaction causes decoherence almost instantly, collapsing any possible blur long before it could ever be noticed. The cat, thankfully, is never truly caught between two states at once. Only carefully isolated, tiny systems can hold a superposition long enough to matter. The strangeness stays quietly confined to the smallest of scales, exactly where it belongs. One of the earliest ways physicists made sense of all this is called the Copenhagen interpretation. It suggests that a particle genuinely has no definite state until it is measured, at which point the wave function collapses into one outcome. This view treats measurement itself as a special, almost sacred act, one that finally makes reality concrete. For decades, it was the most widely taught explanation in physics classrooms around the world. It offers a calm, practical peace, even if it leaves some deeper questions gently unanswered. A different, quieter idea suggests that the wave function never actually collapses at all. Instead, every possible outcome simply happens, each in its own separate, branching universe. In one universe, the atom decays. In another, equally real universe, it does not. You experience only one branch, unaware of all the quiet, parallel versions unfolding elsewhere. It is a vast and strange idea, but it removes the need for any sudden, mysterious collapse at all. Another gentle alternative is called pilot wave theory, first proposed by Louis de Broglie and later developed by David Bohm. In this view, particles always have a definite position, guided invisibly by an underlying wave. There is no true randomness, only a hidden guidance we simply cannot fully observe or predict. This idea keeps a comforting sense of determinism at the cost of the wave becoming a strange, invisible guide. Different physicists have found comfort in different pictures, each equally consistent with what we can measure. It may seem strange that physicists still disagree about what quantum mechanics truly means after a century of study. The reason is simple. Every major interpretation makes exactly the same testable predictions. No experiment has yet been found that can favor one picture cleanly over another. So physicists continue calculating with the same shared mathematics, while quietly disagreeing about the deeper story behind it. Perhaps, for now, it is enough to know the equations work, even while their meaning stays gently unsettled. There is something almost restful in accepting that even experts do not fully agree on what reality is doing underneath. It means not understanding everything perfectly is not a personal failure. It is simply the current shape of human knowledge. The cat in the box, whichever interpretation you prefer, reminds us that not all mysteries need solving tonight. Some can simply be held, gently, like a question you are comfortable falling asleep beside. Let the unopened box rest quietly in your mind, undisturbed until morning. So far, we have spoken mostly of particles, small and definite, if strange. But modern physics suggests something even deeper, that particles themselves are not the most fundamental thing at all. Beneath every particle lies something called a quantum field, invisible and spread throughout all of space. A particle, in this view, is simply a small ripple, a brief excitement, rising from its underlying field. Let us drift a little deeper into the quiet fields beneath the particles. A field in physics is simply something that has a value everywhere in space, even where nothing seems to be happening. You already know one familiar example, the invisible magnetic field that quietly surrounds a refrigerator magnet. Quantum fields work in a similar way, but they fill the entirety of space, everywhere, all the time. Every type of particle, electrons, photons, quarks, has its own dedicated field spread across the universe. You are, in this sense, standing gently inside an invisible ocean of overlapping fields right now. In quantum field theory, a particle is best understood as a small, localized ripple in its underlying field. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. When two particles collide and seem to create a new particle, what is truly happening is energy passing between two rippling fields. Nothing solid is truly colliding, only patterns of energy quietly rearranging themselves. The universe, at its deepest level, may be less like billiard balls and more like an endless, gentle sea. The most familiar quantum field is the electromagnetic field, responsible for both light and electricity. Every photon that has ever reached your eyes was a small ripple traveling through this single, vast field. The soft light of a candle and the sharp light of the sun are both simply different intensities of the very same underlying sea. This field stretches across the entire visible universe, connecting every star to every quiet room. Light tonight is one field's gentle whisper reaching all the way to you. Quantum field theory also reshapes how we understand forces, like the pull between two magnets. Forces are no longer simply invisible tugs across empty space, but the exchange of tiny particles between two fields. Two electrons repel each other by quietly exchanging photons back and forth, like an invisible, constant conversation. Every push and pull you have ever felt may ultimately be built from countless tiny exchanges like this. Even the firmest handshake hides an ocean of quiet, invisible messages passing between fields. One particular field, called the Higgs field, fills the entire universe and interacts with nearly every other particle. Particles that interact strongly with this field behave as though they carry more mass. Particles that barely interact with it, like the photon, remain essentially massless, moving always at the speed of light. In this gentle sense, mass itself is simply a measure of how strongly something is held by an invisible field. Every bit of weight you feel tonight is, in part, a quiet conversation with this single ancient field. In 2012, scientists at a massive underground laboratory in Switzerland confirmed the existence of the Higgs particle. This ripple in the Higgs field had been predicted decades earlier, but never directly observed. Finding it required smashing particles together at enormous energies, deep beneath the quiet countryside. The discovery confirmed one of the last missing pieces of our understanding of quantum fields. A field theorized quietly on paper for 50 years finally rippled, once where scientists could see it. These quantum fields are believed to have existed since the very earliest moments of the universe. Long before atoms, or stars, or planets ever formed, the fields were already quietly filling all of space. Everything that would ever exist was already, in some sense, waiting gently within them. Matter, light, and even you are simply later ripples, rising from something far older than any star. You are quietly a recent wave in a very ancient sea. You might imagine all of space as a vast, still ocean, invisible and endlessly patient. Every particle that has ever existed is simply a small, temporary ripple across its surface. Ripples rise, travel gently, and eventually settle back into stillness. The ocean itself remains quiet and unbroken, no matter how many ripples pass through it. Perhaps your own thoughts tonight are simply gentle ripples too, rising and settling over a deeper, quieter stillness. If particles are ripples in fields, a curious question follows. What happens when there are no ripples at all? Is a place with no particles truly empty, truly silent, truly still? The answer, gently, is no, not entirely. Even in perfect emptiness, the fields themselves are never fully at rest. Let us drift now into that strange, restless quiet known as the vacuum. For centuries, empty space was assumed to be exactly that, empty, a perfect and total nothing. Quantum field theory quietly overturned this idea completely. Even in a perfect vacuum, with no atoms, no light, no matter at all, the underlying fields still gently fluctuate. These fluctuations are small and mostly invisible, but they are never fully absent. True nothingness, it turns out, may not exist anywhere in this universe. These tiny fluctuations occasionally produce what physicists call virtual particles, brief, flickering pairs that appear and vanish almost instantly. A particle and its opposite, an antiparticle, can appear together from nothing, only to meet and vanish again a moment later. They exist so briefly, borrowing energy so fleetingly, that the uncertainty principle simply allows it and asks no questions. This constant, quiet flickering happens everywhere, in every cubic inch of space, including the space around you right now. The emptiness around you tonight is, in truth, gently and constantly alive. This restless vacuum is not just theory. Its effects have been measured directly, in careful experiments. When two mirrors are placed extremely close together, certain vacuum fluctuations are gently excluded from the narrow gap between them. This slight imbalance creates a real, measurable force, quietly pushing the two mirrors together. This is called the Casimir effect, named for the physicist who first predicted it. Even the empty space between two plates can, quietly, gently push. Even at the coldest possible temperature, absolute zero, quantum fields never come to a complete and total stillness. A small residual motion always remains, called zero-point energy. This is not simply leftover heat, it is a fundamental consequence of the uncertainty principle itself. Perfect stillness, it seems, would require perfect knowledge, which the universe never quite allows. Even in the coldest, quietest corner of the universe, something small remains gently, endlessly humming. Some physicists suspect this restless vacuum energy may be connected to one of astronomy's biggest mysteries, dark energy. Dark energy is the strange, invisible influence causing the expansion of the universe to accelerate. Calculations linking vacuum energy directly to dark energy have so far produced wildly mismatched numbers, a puzzle still unresolved. It remains one of the largest open questions, connecting the smallest scales to the very largest. The quiet hum beneath empty space may yet explain why galaxies drift ever further apart. It is a strange comfort, in its own way, to learn that nothing is never truly nothing. Even in the stillest, emptiest room, fields hum quietly beneath the silence. Even in the darkest, most distant reaches of space, something small continues gently to flicker. Perhaps stillness was never truly the absence of motion, only motion too soft and too small to notice. Rest tonight does not require true emptiness, only a quiet enough hum to finally let go. We now turn from the deepest theory towards something far more practical, quantum computing. For decades, this remained an abstract idea, discussed only in university lecture halls. Today, working prototypes already exist, quietly humming in specialized laboratories around the world. They promise to reshape entire fields, from medicine to cryptography, in the coming decades. Let us walk gently through what makes these strange machines so different. An ordinary computer stores information using bits, each one simply a 0 or a 1. A quantum computer instead uses qubits, which can exist in a superposition of 0 and 1 at the same time. This is not simply a faster version of a normal bit. It is a fundamentally different kind of information. A single qubit quietly holds two possibilities, gently overlapping until it is finally measured. The smallest unit of quantum information already carries a little of the universe's own uncertainty inside it. The true power of qubits appears when many of them are linked together through entanglement. Two entangled qubits can represent four possibilities simultaneously. Three qubits can represent eight, and so on. This growth is exponential, doubling with every additional qubit added to the system. A few hundred well-behaved qubits could, in principle, represent more possibilities than there are atoms in the observable universe. A small, quiet machine, holding numbers larger than the universe itself, can easily contain. Quantum computers are not simply faster at everything. Ordinary tasks, like writing an email, remain unchanged. They excel instead at very specific kinds of problems, particularly searching, optimizing, and simulating other quantum systems. Simulating a complex molecule, for instance, is remarkably difficult for ordinary computers, but far more natural for a quantum one. This could one day accelerate the discovery of new medicines and materials considerably. A machine built from uncertainty may end up helping us understand chemistry more clearly than ever before. Qubits are remarkably fragile, easily disturbed by heat, vibration, or even stray electromagnetic noise. This is the same decoherence we spoke of earlier, information quietly leaking away into the environment. To keep qubits stable, many quantum computers are cooled to temperatures colder than deep space itself. Even then, calculations must often be completed in mere fractions of a second before the fragile state dissolves. These machines work at the very edge of stillness, in rooms colder than the space between stars. Entanglement also allows for a new kind of secure communication, called quantum encryption. Any attempt to secretly observe an entangled message immediately and detectably disturbs it. This means eavesdropping is not just difficult, it becomes, in principle, physically impossible to hide. Several countries have already tested secure quantum communication between ground stations and orbiting satellites. A message protected not by a clever code, but by the quiet, watchful laws of physics itself. The first working quantum bits were demonstrated only in the 1990s, fragile and difficult to control. Today, machines with hundreds of qubits already operate in research labs across the world. Progress remains slow and careful, each additional stable qubit a genuine, hard-won achievement. Yet the field has grown from a theoretical curiosity into a serious global technological race. A once impossible idea, quietly, patiently, becoming real, one careful qubit at a time. It is worth remembering that quantum computers will likely never fully replace ordinary computers. For most everyday tasks, classical computers remain simpler, cheaper, and perfectly sufficient. Quantum machines are best understood as specialized tools, reserved for a narrow set of extraordinarily difficult problems. Even the strangest new technology tends to find its place quietly beside the old, rather than replacing it entirely. Some problems need a stranger kind of machine, but most of life remains comfortably, familiarly ordinary. Having wandered through strange new machines, let us turn now toward something warmer, quantum effects inside living things. For a long time, Quantum physics was assumed to matter only for cold, careful laboratories. But nature, it turns out, may have been quietly using these same tricks for billions of years. Long before humans built a single quantum computer, life may have already built its own. Let us drift gently into the quantum biology of the living world. Inside a green leaf, sunlight is captured and guided toward tiny reaction centers with remarkable efficiency. Scientists have found evidence that this energy may travel using a quantum effect called coherence, briefly exploring multiple paths at once. By sampling many possible routes simultaneously, the energy may find the most efficient path almost instantly. Warm, wet, chaotic leaves seem an unlikely place for delicate quantum effects to survive, and yet they may. Every quiet green leaf outside your window may be running a small, ancient quantum calculation. Many migratory birds can sense the Earth's magnetic field, guiding their long journeys across entire continents. One leading theory suggests a special protein in their eyes creates a pair of entangled electrons in response to light. The Earth's gentle magnetic field subtly influences this entangled pair, possibly allowing the bird to sense direction. If true, some birds may be quietly using quantum entanglement simply to find their way home. A journey across half the world, guided by one of the strangest effects in all of physics. Even the sense of smell may quietly involve quantum effects, according to one intriguing theory. Traditional explanations suggest smell depends only on the shape of a molecule fitting into a receptor. An alternative idea suggests your nose may also detect the quantum vibrations of a molecule, using a tunneling effect similar to what we explored earlier. This remains a debated, gently unresolved corner of biology and physics working closely together. Perhaps the next quiet scent that reaches you tonight carries a small quantum story of its own. What is striking about quantum biology is how carefully life seems to walk a narrow, delicate line. Quantum effects are fragile, easily destroyed by heat and disorder, and living things are warm, messy, and constantly moving. Yet somehow, in small, precise pockets, delicate quantum behavior survives just long enough to be useful. Evolution, across billions of patient years, may have quietly discovered tricks physicists are only now beginning to understand. Nature, it seems, was experimenting with the strange and the quantum long before we ever gave it a name. Quantum biology offers a quiet, comforting bridge between the strange, small world and our own familiar, breathing one. It suggests the uncertainty and superposition we have explored tonight are not confined only to sterile laboratories. They may already be gently woven into leaves, feathers, and the quiet workings of your own senses. The strange world we have traveled through was never as distant from you as it first seemed. It has, perhaps, been resting quietly inside living things all along. Every particle of ordinary matter has a mirror twin, called its antiparticle, identical in mass, but opposite in charge. The electron's twin is called a positron, carrying the very same mass, but a gentle positive charge instead. When a particle meets its antiparticle, the two do not simply collide, they quietly annihilate, turning fully into pure energy. This is one of the few processes where matter converts completely into light, with nothing solid left behind. Somewhere in the universe, matter always carries a quiet mirror, waiting patiently to meet it. In the earliest moments after the beginning of the universe, matter and antimatter should have been created in exactly equal amounts. If that were perfectly true, they should have annihilated each other completely, leaving behind only light and nothing more. Yet here you are, made of matter, in a universe still full of stars and stone and quiet breathing. For every billion pairs that vanished into light, it seems one lonely particle of matter was left over. Everything you have ever known is built from that tiny, patient imbalance. Antimatter is not only found in laboratories, small traces occur naturally, even inside living things. A banana, rich in potassium, releases a positron roughly once every 75 minutes from a rare natural decay. Your own body, containing potassium as well, quietly does the very same thing, far too rarely and faintly to ever notice. These tiny antimatter particles annihilate almost instantly, harmlessly, into the gentlest flicker of light. Even your quiet body carries a faint, sleepy echo of the universe's oldest mystery. Antimatter already has a gentle, practical use inside hospitals in a scanning technique called a PET scan. A patient is given a small amount of a substance that releases positrons, antimatter's electron twin, from within the body. When each positron meets an electron, it releases a tiny, precise flash of light, tracked carefully by the scanner. These small flashes let doctors quietly build a detailed picture of what is happening deep inside the body. One of physics' strangest ideas now quietly helps doctors see and heal more clearly. Far above the Earth, cosmic rays, energetic particles from deep space, constantly rain down upon our atmosphere. When these particles collide with air molecules, they sometimes create brief flashes of antimatter high above your head. These antimatter particles exist only for the briefest instant before meeting ordinary matter and gently vanishing again. Detectors on satellites and mountaintops quietly capture evidence of this constant, invisible shower. Tonight, high above the clouds, tiny mirrors of matter are still quietly appearing and fading. Antimatter cannot simply be placed in an ordinary container, since it would instantly annihilate upon touching ordinary matter. Scientists instead trap it using carefully shaped magnetic and electric fields, holding it gently apart from any container wall. At the largest physics laboratory in Europe, researchers have successfully held antimatter atoms suspended this way for many minutes at a time. It is an extraordinarily delicate kind of care, holding something that vanishes the instant it is touched. Some things in this universe can only ever be held gently, never grasped. Physicists still search for the small, subtle difference that once tipped the balance between matter and antimatter. Some experiments have found tiny asymmetries in how certain particles decay, hinting at part of the answer. The full explanation, however, remains one of the most patiently pursued mysteries in modern physics. Somewhere in the earliest fraction of a second, the universe quietly chose to leave a little matter behind. We are, in a very real sense, the leftover of an ancient and gentle imbalance. Because matter and antimatter release so much energy upon meeting, antimatter is sometimes imagined as a future fuel for deep space travel. In principle, a small amount could release more energy than any chemical fuel ever could. In practice, antimatter is extraordinarily difficult and costly to produce, and even harder to store safely in large amounts. For now, it remains a quiet dream for future engineers, rather than a working technology. Perhaps one distant day, ships will drift between stars, powered by matter's oldest, gentlest mirror. Antimatter reminds us that even the universe's simplest particles come with a hidden opposite, waiting quietly nearby. Nothing exists entirely alone. Every piece of matter carries the shadow of what it could have been instead. And yet, from that constant meeting of opposites, enough matter remained to build stars and oceans and quiet bedrooms. Balance, it seems, does not always mean equal. Sometimes it simply means enough was left over to continue. Let that quiet leftover carry you gently toward our next small mystery. It seems obvious that two solid objects cannot occupy the same place at once, but the deeper reason is a quiet quantum rule. Electrons, along with several other particles, obey something called the Pauli exclusion principle. It states, gently but firmly, that no two identical particles of this kind can occupy the exact same quantum state at once. This is the quiet reason your hand does not pass through the blanket you are resting beneath. Solidity itself is simply countless electrons, patiently refusing to share the very same space. Because electrons cannot share the same state, they arrange themselves into layers, called shells, around every atomic nucleus. Each shell holds only a limited number of electrons before the next must begin filling a new, slightly further layer. This quiet, orderly stacking is the reason different elements behave so differently from one another. It is why oxygen bonds so easily, while noble gases like helium remain calm and unreactive. The entire chart of chemistry rests gently on this one quiet quantum rule. Physicists divide all particles into two gentle families, called fermions and bosons. Fermions, including electrons and protons, are the particles that obey the exclusion principle, refusing to share a state. Bosons, including photons, are far more sociable and can happily pile into the very same state together. This is part of why laser light can be made of countless photons, all moving in perfect, identical step. Some particles insist on privacy, others are content to share every quiet moment together. The exclusion principle does more than shape atoms. It can hold up an entire dying star. When a star like the Sun exhausts its fuel, gravity tries to crush its core down to an infinitely small point. The electrons inside quietly resist, refusing to be squeezed into the same state, creating a firm, outward quantum pressure. This pressure alone can be enough to halt the collapse, leaving behind a small, dense ember called a white dwarf. A single quiet quantum rule can be strong enough to hold up the weight of an entire star. For even heavier dying stars, gravity is strong enough to overcome the resistance of electrons entirely. Electrons and protons are crushed together, forming neutrons, which then quietly take up the resistance themselves. The result is a neutron star, so dense that a single teaspoon could weigh more than a mountain. Even at this extraordinary density, the same gentle quantum rule holds the star from collapsing further. The smallest rule in physics can, it turns out, support the heaviest of burdens. One deeply strange aspect of quantum physics is that identical particles are not merely similar, they are perfectly, completely identical. Every electron in the universe is utterly indistinguishable from every other electron, with no hidden serial number, no tiny scratch to tell them apart. This is unlike anything in our ordinary experience, where even identical-looking twins can always be told apart eventually. This perfect sameness is part of why the exclusion principle works so precisely. with no exceptions anywhere. Somewhere in the universe, true, perfect sameness quietly exists, even if only among its smallest pieces. When atoms are cooled to temperatures near absolute zero, their quantum nature becomes strikingly visible. Certain atoms, cooled enough, can merge into a single strange state called a Bose-Einstein condensate, behaving as one shared quantum entity. In this state, countless individual atoms lose their separate identities, moving together as a single, gentle wave. It is one of the coldest, quietest states that matter can ever reach. At the very edge of stillness, many small things can quietly become one large, shared calm. You might think of the exclusion principle as a quiet kind of courtesy built into the fabric of matter itself. Each electron, in its own small way, simply steps aside, making room for every other to have its own quiet place. From that simple courtesy, atoms hold their shape, chemistry finds its structure, and stars find their support. Perhaps there is something worth carrying from that into your own quiet rest tonight. Even in the smallest of spaces, there is usually room enough if everything simply steps gently aside. We have now seen how one quiet rule shapes atoms, chemistry, dying stars, and the coldest matter known. From here, let us drift outward, away from atoms entirely, toward the birth of the universe itself. For quantum uncertainty, it turns out, may have shaped even the largest structures in the sky. Let us travel back, gently, to the very beginning of everything. A single, quiet moment, before even light had learned to travel freely. Nearly 14 billion years ago, the entire observable universe is believed to have been compressed into an unimaginably small, dense point. In that first sliver of a moment, quantum effects were not confined to atoms, they governed the whole of existence. The uncertainty we explored earlier tonight was not a small detail. It was, briefly, the entire rulebook of reality. Everything that would ever exist was folded into a space smaller than a single atom. The largest thing we know of once fit gently inside the smallest imaginable space. In that earliest moment, tiny quantum fluctuations, the same restless flickers we found earlier in empty space, rippled through the newborn universe. These fluctuations created faint, uneven patches, some very slightly denser than others. As the universe expanded rapidly, these tiny unevenness were stretched, gently, across vast distances. Without this quantum unevenness, matter might have spread perfectly evenly, and stars may never have formed at all. Every galaxy above you tonight may trace its very first outline back to a quiet quantum flicker. The faint afterglow of this early universe still surrounds us today, called the cosmic microwave background. This gentle radiation carries a faint, mottled pattern, tiny variations in temperature across the sky. These variations are, in effect, a photograph of those ancient quantum fluctuations, frozen in place for billions of years. Scientists have mapped this pattern with extraordinary precision, finding it exactly matches quantum predictions. The oldest light in the universe still quietly carries the fingerprints of its smallest, earliest uncertainty. Over billions of patient years, those slightly denser quantum patches slowly pulled in more and more surrounding matter through gravity. Denser regions grew steadily denser still, eventually collapsing gently into the first stars and galaxies. Without that first, tiny unevenness, gravity would have had nothing uneven to gather around. The vast cosmic web of galaxies you might imagine tonight began as something smaller than a single particle. From the smallest possible flicker, the largest structures in existence were quietly, patiently born. Many cosmologists believe the universe underwent a period of extraordinarily rapid expansion, called inflation, in its very first fraction of a second. During this brief and violent stretching, tiny quantum fluctuations were blown up to scales far larger than they began. A flicker once smaller than an atom could, in this way, become the size of an entire galaxy cluster. It remains an active, carefully studied area of cosmology, still gently being refined and tested. Somewhere in that first instant, the smallest uncertainty was stretched into the shape of everything we see. It is a strange and gentle thought that galaxies exist partly because the universe could not know its own density perfectly, even for an instant. If the early universe had been perfectly smooth, with no uncertainty anywhere, it might have remained forever empty and even. Instead, its own quiet fuzziness gave it just enough unevenness to grow into stars and planets, and eventually, quiet rooms like this one. Uncertainty, it seems, was not an obstacle to creation. It was one of its gentlest ingredients. Perhaps not knowing everything perfectly is not only survivable, but sometimes, quietly, generative. We have now traveled from the smallest quantum flicker to the largest structures the universe contains. Let us return, gently, closer to home, toward the particle of light itself, and the strange edge where quantum physics meets relativity. A particle that never ages, and never truly experiences the passage of time at all. Let us follow it for a while, quietly and at the very edge of speed itself. According to relativity, the faster something travels, the slower time passes for it, relative to someone standing still. A photon, the particle of light, always travels at the ultimate speed limit of the universe. For light itself, in a strange and gentle sense, no time passes at all, however far it travels. A photon that left a star 1 billion years ago experiences its entire journey as a single, timeless instant. Some of the oldest light in the sky has, in its own strange way, never aged a single moment. Photons are entirely massless, one of the few particles in the universe with absolutely no rest mass at all. This is precisely why they are able to travel at light's own speed, since anything with mass would require infinite energy to do the same. Yet despite having no mass, a photon still carries real energy and momentum, capable of gently pushing objects it strikes. Solar sails, a quiet future technology, aim to use this faint push to glide spacecraft gently through space. Something entirely without weight can, patiently, still gently move the world. Although photons have no mass, their path can still be gently bent by the gravity of massive objects, like stars. This happens because gravity, in relativity, is not truly a pull, but a gentle curving of space itself. Light simply follows the smoothest available path, which curves wherever massive objects quietly bend the space around them. This bending has been measured precisely, confirming one of Einstein's most striking predictions. Even light, moving at its own unmatched speed, still gently follows the shape of the space it travels through. Einstein's most famous equation quietly states that energy and mass are in truth two forms of the very same thing. A small amount of mass, converted fully, releases an extraordinarily large amount of energy. This is the same principle behind the annihilation of matter and antimatter we explored earlier tonight. It is also the quiet source of the sun's warmth, as tiny amounts of mass are steadily converted into light. Mass and energy, it turns out, were never truly two separate things at all. Quantum physics and relativity each describe the universe with extraordinary precision in their own separate domains. Quantum physics governs the extremely small, while relativity governs the extremely fast and the extremely massive. In most situations, physicists can use one theory or the other without needing them both at once. But in a few extreme places, like the center of a black hole, both theories are needed together, and they do not yet agree. Somewhere at the edge of the smallest and the fastest, physics is still quietly searching for common ground. This unfinished bridge between quantum physics and relativity remains one of the greatest open questions in all of science. Physicists have proposed several careful ideas to unite them, though none has yet been confirmed by experiment. It is a reminder that even our best, most tested theories still have quiet, unfinished edges. Perhaps some bridges take longer than a single lifetime to finish building. For now, we can rest gently on either side and let future minds continue the quiet work. We have followed light across billions of years and found it strangely untouched by time itself. Let us return now to something closer to home, the quiet, careful work of keeping messages truly secret. A future built not on clever codes, but on the delicate laws of physics themselves. Let us drift toward it gently now. The quiet architecture of a more private tomorrow. Nearly all of today's private communication, from banking to messages between friends, relies on mathematical codes that are difficult but not impossible to break. A sufficiently powerful quantum computer could, in principle, break some of these codes far faster than any ordinary computer. This has led governments and companies alike to quietly prepare for a future where today's encryption may no longer be safe. Researchers are now designing new kinds of codes built to resist even quantum computers. A quiet race is already underway between one kind of quantum power and another. One elegant solution uses quantum physics itself to protect information rather than simply outrunning it. This method, called quantum key distribution, uses entangled or carefully prepared photons to share a secret code between two parties. Any attempt to secretly intercept these photons would disturb them in a way that is immediately, unavoidably detectable. This means the two parties can always know, with certainty, whether their secret has been touched. For the first time, secrecy can be protected not just by cleverness, but by the quiet laws of physics itself. In 2017, a Chinese satellite named Micius successfully distributed entangled photons between two ground stations over 1,000 miles apart. This demonstrated that quantum-secured communication could work not just across a laboratory table, but across an entire continent. It marked a major, quiet milestone toward a future global network built on quantum security. Several countries have since begun testing similar quantum communication networks of their own. High above the clouds tonight, satellites already carry secrets protected by the strangest rules in physics. Researchers are now quietly working towards something called a quantum internet, linking distant quantum computers directly through entanglement. Such a network could allow perfectly secure communication and let distant quantum computers work together on shared problems. Early, small-scale versions of this network already connect a handful of laboratories in careful, controlled experiments. A fully global quantum internet likely remains decades away, built patiently, one careful link at a time. Somewhere in the future, entangled light may quietly carry our messages between distant, waiting machines. Quantum physics also offers something surprisingly rare, a source of truly, fundamentally random numbers. Ordinary computers can only generate numbers that appear random, following hidden, predictable patterns underneath. Quantum devices, by measuring properties like a photon's path, can generate numbers that are genuinely unpredictable, even in principle. This kind of true randomness is valuable for security systems that must never be predicted or guessed. Even the deepest uncertainty of nature has quietly found a gentle, practical use. We have seen how the same strangeness that unsettled Einstein now quietly protects messages sent across oceans and satellites. From here, let us turn toward the quiet people who first uncovered these strange and gentle rules. Not as distant historical figures, but as curious minds, working late, uncertain, and patient, just like anyone else. Let us walk gently through their story now. The quiet human history behind tonight's strange and gentle physics. Max Planck did not set out to overturn physics. He was simply trying to solve one stubborn, technical puzzle about glowing objects. He later admitted that he treated his own idea of energy packets as a mathematical trick, not a description of real, physical reality. For years, he remained quietly uneasy about the implications of what he had found. It would take other physicists, building carefully on his work, to reveal how deep his small idea truly ran. Sometimes, the largest discoveries begin as a quiet, reluctant answer to a small, technical problem. In 1913, Danish physicist Niels Bohr proposed that electrons orbit the nucleus only at certain fixed, permitted distances. This simple model successfully explained the specific colors of light that different elements emit when heated. Bohr later became a central, quiet mentor to an entire generation of young quantum physicists. He was known for his patient, careful thinking, often spending long hours quietly wrestling with a single idea. Some of the deepest ideas in physics were built slowly, through quiet patience, rather than sudden flashes of certainty. In 1926, while on a quiet winter retreat, Erwin Schrödinger developed the equation that now bears his name. This equation precisely describes how a particle's wave function evolves gently over time. It remains, to this day, one of the most important and most used equations in all of physics. Schrödinger himself later expressed quiet discomfort with some of the stranger implications of his own equation, including his famous cat. Even the ones who build the strangest ideas do not always feel entirely at ease with them. Werner Heisenberg developed much of his early quantum theory while recovering from a bout of hay fever on a quiet, isolated island. Away from the noise and distraction of university life, he found the quiet space to think clearly about the strange new mathematics. He later described feeling a sense of vertigo, gazing through nature's small atomic surface into something stranger underneath. His work there quietly laid one of the foundational pillars of quantum theory. Sometimes the clearest thinking arrives only after the noise of the world has gently quieted. Though best known for her work on radioactivity, Marie Curie's careful research quietly helped lay groundwork for the quantum understanding of the atom. She was the first person ever to win 2 Nobel Prizes in 2 entirely different scientific fields. Her careful, patient laboratory work helped reveal that atoms were not simple, indivisible objects after all. She worked for years, quietly, often in difficult conditions, driven simply by careful curiosity. Some of the deepest doors into the atom were first opened by patient, quiet persistence. Paul Dirac was known among his colleagues for his extraordinary quietness, often going hours without speaking a single word. Despite this quiet nature, his equations combining quantum physics and relativity were remarkably elegant and predicted the existence of antimatter. When antimatter was later discovered in the laboratory, exactly as his equations suggested, it confirmed one of the most striking predictions in physics history. Dirac once said he believed a physical law should be beautiful before it is even tested. Sometimes the quietest people carry the loudest, most far-reaching ideas. Richard Feynman approached quantum physics with a rare sense of playful curiosity, treating even its strangest puzzles like games worth enjoying. He developed simple diagrams, now named after him, that make complex particle interactions far easier to picture and calculate. He was famous for insisting that nobody, not even the experts, truly understands quantum mechanics, only how to use it. He found comfort, rather than distress, in admitting the limits of even his own deep understanding. Perhaps not fully understanding, something can still be enjoyed quietly, like a good and curious puzzle. Alongside the well-known names, several women made careful, quiet contributions often overlooked by history for many years. Physicist Emmy Noether developed a theorem connecting symmetry and conservation laws, a quiet foundation beneath much of modern physics. Physicist Lise Meitner helped explain nuclear fission, though the Nobel Prize for the discovery was awarded only to her male colleague. Their careful, patient work quietly shaped the field, even when recognition arrived late or not at all. Some of the quietest names in physics carried some of its heaviest, most important ideas. In the 1920s, the world's leading physicists gathered periodically at a quiet conference in Brussels, called the Solvay Conference. These meetings became famous for intense, careful debates between physicists like Einstein and Bohr over what quantum physics truly meant. A single surviving photograph shows an extraordinary gathering, nearly every attendee eventually winning a Nobel Prize of their own. These quiet, patient debates helped shape the interpretations physicists still discuss carefully today. Some of the deepest ideas in physics were settled slowly, over quiet conversation, rather than sudden agreement. Looking back across these quiet lives, a gentle pattern emerges. Discovery rarely arrives as a single, sudden flash. It comes instead through patient uncertainty, quiet retreats, careful arguments, and years of steady, humble work. Even the greatest minds in this story often felt unsettled, uncertain, and quietly unsure of their own conclusions. That uncertainty, it turns out, was not a weakness in their character, but simply an honest response to something genuinely strange. Perhaps you can allow yourself that same gentle uncertainty tonight and rest just as easily within it. These patient, curious people built the strange and gentle world we have wandered through tonight. Let us turn now toward one final, unfinished question, the very largest puzzle their work has left behind. A search still continuing quietly today, in laboratories and quiet offices around the world. The search for one single, unified theory of everything. Let us drift toward it now, gently, and without any rush to arrive. Modern physics rests on two extraordinarily successful theories: quantum physics for the very small, and general relativity for gravity and the very large. Each has been tested with extraordinary precision, and neither has ever failed a careful experiment. And yet, when physicists try to combine them directly, the mathematics quietly breaks down into nonsense. Somewhere, one gentle idea is still missing, one that would let both theories rest comfortably together. Physics, in this sense, is still quietly searching for its own missing piece. This missing unified idea is often called quantum gravity, a theory that does not yet exist in finished form. It would need to describe gravity itself, using the same quantum rules that govern particles and fields. Several careful, patient approaches have been proposed, though none has yet been confirmed by direct experiment. It remains one of the most difficult and most quietly pursued questions in modern physics. Somewhere between gravity and the quantum world, physics is still gently listening for an answer. One proposed approach, called string theory, suggests that every particle is actually a tiny, vibrating string of energy. Different vibrations, in this view, produce the different particles we observe, much like different notes from the same instrument. The theory requires several additional, hidden dimensions of space, curled up far too small for us to ever notice directly. It remains elegant and mathematically rich, though it has not yet been confirmed by any direct experimental test. Perhaps underneath everything, the universe is simply a quiet, patient kind of music. A different approach, called loop quantum gravity, suggests that space itself is not smooth, but built from tiny, discrete loops. In this view, even space comes in small, countable packets, much like energy does in ordinary quantum physics. This would mean there is a smallest possible distance, beneath which space simply has no further meaning. Like string theory, it remains a serious, careful hypothesis, still awaiting confirmation. Perhaps even the empty space around your bed tonight is quietly built from countless small, patient stitches. Black holes sit exactly at the uneasy border between quantum physics and gravity, where both theories are needed and neither fully agrees. Physicist Stephen Hawking showed that black holes may slowly release a faint, quantum glow, now called Hawking radiation. This suggests that even black holes, over unimaginably long spans of time, eventually fade and evaporate away. This discovery deepened, rather than resolved, the tension between our two greatest theories. Even the universe's darkest, heaviest objects are still gently, patiently, whispering with quantum uncertainty. If a black hole eventually evaporates completely away, a strange question follows: what happens to everything that ever fell inside it? Quantum physics insists that information can never truly be destroyed, only transformed or rearranged. This creates a deep, gentle puzzle known as the black hole information paradox, still debated carefully among physicists. Some suggest the missing information leaks out slowly, hidden quietly within the faint glow of Hawking radiation. Even in the darkest, most crushing places in the universe, nothing may ever be entirely, permanently lost. A completed theory of everything would not change your daily life directly. The ordinary world would remain exactly as familiar as it is tonight. But it would answer some of the deepest remaining questions, about the earliest moment of the universe and the deepest nature of space itself. It would be less a practical tool and more a quiet, complete portrait of existence itself. Physicists continue this search, patiently, knowing it may take many more careful generations to complete. Some portraits are simply worth the patience, however long they take to finish. There is something quietly comforting in knowing that even physics, humanity's most precise science, still has an unfinished corner. It means uncertainty is not a personal failing, but simply the honest, ongoing shape of understanding itself. The smartest minds in history worked their whole lives on pieces of this puzzle and passed the remainder on gently to those who followed. You, too, are allowed to leave certain questions unfinished tonight and simply rest beside them. Some puzzles are meant to be carried forward gently, rather than solved before sleep. Perhaps the search for a theory of everything says as much about curiosity as it does about the universe. It is a quiet, patient reaching toward understanding, without any guarantee of ever fully arriving. And yet, generation after generation, physicists continue reaching anyway, gently, and without complaint. There is something deeply human in that quiet, unfinished reaching. Let us carry a little of that patience with us now, as we drift toward the end of tonight's journey. Throughout tonight's journey, one quiet thread keeps reappearing, the strange role of observation itself. Again and again, we have seen that measuring, watching, or gathering information changes what unfolds. This raises a deep and gentle question about the relationship between the universe and whoever, or whatever, is paying attention to it. Physicists still debate exactly what counts as a true observation and why it matters so much. Let us sit with this question a little longer as we drift toward the end of tonight's journey. An observer in physics does not need to be a person or even a conscious mind at all. A single grain of dust, a stray photon, or a simple detector can all serve as an observer in the sense that matters here. What truly matters is whether information about a system has become recorded anywhere in any form. Once recorded, even quietly, even unread by any person, the superposition softly gives way. The universe, it seems, is simply, endlessly keeping track of itself. Some physicists now believe information itself may be more fundamental than matter or energy. In this view, particles, fields, and forces are simply the way information organizes and expresses itself. This remains a genuinely open question, discussed carefully among physicists studying the deepest foundations of reality. Perhaps underneath everything, the universe is less like solid matter and more like a vast, quiet, unfolding message. One we are all, in some small way, quietly helping to write. Physicists refer to this deep puzzle as the measurement problem, one of the most enduring open questions in the field. It asks, quite simply, what exactly counts as a measurement, and why measurement alone seems able to collapse possibility into fact. No experiment yet has fully settled the question, despite a century of careful, patient work. It remains one of physics' quietest, most persistent mysteries. Some doors in science stay open for a very long time, and that too is a kind of progress. There is something quietly moving in the idea that the universe, at its smallest scales, seems to respond to being noticed. Not because it is alive or aware in any way we would recognize, but because information and reality seem to be tied together more closely than we ever expected. The simple act of looking is never quite as passive as it feels. Perhaps every quiet glance we take at the world leaves the faintest mark upon it. It is worth remembering, gently, that none of tonight's strangeness reaches into your everyday life directly. Your bed remains solid, your breathing remains steady, your body remains firmly, comfortably one single, definite thing. The quantum world hums quietly far beneath the surface, shaping atoms without ever disturbing the calm of the world you can touch. You can rest tonight fully within the ordinary world, even while knowing something stranger supports it underneath. The strange and the familiar have always been quietly resting on top of one another. There is a strange comfort in learning that uncertainty is not a flaw in the universe, but a fundamental part of its design. Even the smallest particles are permitted to remain unresolved, gently overlapping, until the moment truly calls for an answer. If the universe itself is patient with not knowing, perhaps our own unresolved thoughts deserve the same quiet patience. Not every question tonight needs to collapse into a single, sharp answer before you can rest. Some things are allowed to stay soft and open until morning gently decides otherwise. Every object around you tonight, your blanket, your pillow, the walls of the room, is built from the same quiet quantum fields we explored earlier. Beneath their calm, solid stillness, countless particles flicker, wave, and softly overlap, exactly as they have for billions of years. You are surrounded, gently, by a hum too small and too fast for any of your senses to ever notice. And yet, somehow, all of that quiet strangeness adds up to something as simple and steady as a warm, comfortable bed. The smallest, strangest parts of the universe have quietly built something large enough to rest inside. Quantum physics, at its heart, is a story about small permissions, small allowances the universe grants itself. It allows a particle to be two things at once, allows information to travel by no clear path, allows barriers to be gently crossed. None of these permissions break the universe. They simply reveal how flexible its foundations truly are. Structure and strangeness, it turns out, were never truly opposites. The universe holds both, quietly, at the very same time. We began tonight far smaller than any place we had visited before, smaller than an atom, smaller than its own quiet nucleus. We watched light behave as both a wave and a particle, watched a single electron pass through two openings at once. We felt the soft, permanent fuzziness of uncertainty and the strange, patient leaking of tunneling through impossible walls. We followed entangled particles across impossible distances and sat quietly with Schrödinger's unopened box. And we found, underneath it all, a universe of fields humming gently, even in the stillest, emptiest space. Not every question we raise tonight has a tidy, finished answer, and that is all right. Physicists still quietly debate what measurement truly means, what happens to the other branches of possibility, what lies beneath the deepest fields. These open questions are not failures. They are simply the edges of what humanity has learned so far. Every unanswered question tonight is also, quietly, an invitation for tomorrow. Science, like sleep, does not require every thread to be tied before it can rest. There is nowhere further tonight for us to travel, no smaller scale left to explore. We have reached the quiet floor beneath all matter, the fields, the fluctuations, the soft, endless hum of possibility. From here, there is only rest, only the slow settling of thought into stillness. Let your own thoughts overlap gently now, unmeasured, unresolved, exactly as a quantum particle rests before it is asked a question. There is no need to collapse anything tonight. And so our slow journey through quantum physics comes gently to an end. Past the wave and the particle, past the uncertain, overlapping possibilities, past the fields that hum quietly beneath all things. We did not solve every mystery tonight, and that was never the point. We simply let the strangeness settle gently into something we could rest beside. Let your own thoughts stay soft and unresolved now, the way a particle rests before it is ever asked a question. Let your breathing settle into its own long, slow rhythm. The fields will keep humming quietly, whether you are here to notice or not. You can rest. This was Sleep Science Drift. Sleep well.